Okay, so let's continue. Last time we gave a brief introduction about this maximum value, minimum value problem. So we introduced the definition. What do you mean local maximum, local minimum, and global maximum, global minimum? And we introduced this famous theorem. Famous theorem basically tells us that if we have a particular point which is a local maximum, local minimum, if it's differentiable at this point, then the derivative must be zero. And this is a very simple from the graph. If you look at the graph over here, if you look at the maximum value or minimum value, if it's differentiable, it's obviously you will always have a horizontal tangent line there, right? So that means at those points, the derivative must be zero. But reversely, it's not true. The derivative equals zero may not imply it has a local maximum or local minimum. So you need to for based on this, we are able to identify those candidates for the local maximum minimum. Those candidates are what we call the critical numbers. So the critical numbers is either the derivative equals zero or the derivative undefined. Like if you have a sharp corner, right? So in that case, the derivative is undefined, but you will still get a local maximum or local minimum in that case. Okay. Speaking of that, so I see a couple of people when they're doing the homework, they notice that there's some question asked about the what's the maximum value or minimum value. When we see maximum value or minimum value, it means the question is asking for the function value. So you need to have the input. You need to have the y value. Okay. So there the question is asked about the y value instead of the position of the x. The position of this maximum or minimum. So the critical number actually give you the candidate position for the maximum value, minimum value. Okay. So this is the things I want to clarify. Last time we also discussed this so-called closed interval method. So closed interval method is one way to find this maximum value, minimum value for a continuous function defined on a closed interval. Okay, and so this is important. Okay, the function must be continuous. That's the first criteria. The second condition is this function must be defined on this closed interval. If it's open, then you may not find the maximum value, minimum value. Okay. One example you can think about is if you have this logarithm function, y equals natural log of x. Say you define the function, so this function is defined on this interval, say between 0, say if you define the function from 0 to 2, right? And we know this function is continuous on this interval, and it's open here. But if you look at the function value as the x is getting closer and closer to 0, this function go to negative infinity. So you cannot find the minimum value in this case. Does this make sense? So that's why we require this. Before you apply this method, you need to make sure the interval is closed. Okay. So For a continuous function defined on a closed interval, this is a guaranteed. You can always find the maximum value, minimum value. And this is what we call the extreme value theorem. Where's the extreme value theorem? Sorry. Yeah, extreme value theorem, we discussed this. Extreme value theorem tells us that if we have a continuous function defined on a closed interval, then this function must have an absolute maximum, absolute minimum. Okay, not like this case, if this is an open interval, okay, or half open, this interval, then you may not find the maximum or minimum in this case. Right, so this is an important condition. But and based on this theorem, we also in order to find the maximum value, minimum value, we have an algorithm to do that. We use this closed interval method. So the idea is first, you find all those candidates for the maximum value, minimum value, meaning you need to find the critical number of the function inside the given interval. So basically you need to solve either the derivative equals 0 or the derivative doesn't exist. Don't forget this part, okay? So that's the first step. The second step is you after you figure out the critical number, remember the critical number give you the positions, the candidate positions of the candidates for the maximum value, minimum value. So you need to plug those numbers into the original function, the function to get the function value. Right? So that will give you the possible maximum value, minimum value. So those are the function values we are looking for. And then you also need to figure out the function value at the end point. Sometimes the maximum, minimum value may happen at the end point, right? So you need to figure out this function value at this end point. And then for all those function value we obtained from these two steps, we can identify which one is the maximum, which one is the minimum. Right. So that's basically what we call the closed interval method. And we did last time we did this example, right? So the first step, you try to find the critical number. Remember the critical number include both the derivative equals 0 or the derivative doesn't exist. So given the derivative function, first of all, you identify the derivative doesn't exist at a point where x equals 0, okay? Or the derivative equals 0, the solving this equation, you get x is equal plus or minus 1. So you get 3 different critical numbers, okay? And notice all these 3 critical numbers are inside this interval. If for some problem, if you find the critical number, if the number is outside the given interval, then we don't care about that, okay? So then you plug all those critical numbers into the function. You figure out the function value here. And then you figure out the function value at the end point. We have 2 endpoints, -3 and 3, right? So you plug everything in there. And then you can determine, so we get 5 values, right? So between these 5 function values, we can figure out which one is the maximum value and which one is the minimum value, and you also know the location of that. Does this make sense? Okay, so this is the closed interval method, and this is the one of the most important method for optimization. Suppose that you have a function and you want to find the maximum value, minimum value, right? And later on, when we talk about the optimization problems, uh, in that case, we are using this approach to identify the maximum value, minimum value. Okay. So there are a couple of more examples. The second example we can we consider here is the function. In this case, the function is the absolute value of x, and and we know this function is continuous, right? So this is a continuous function defined on this interval. Remember, this is a closed interval. That means we can always find a maximum value, minimum value of this, right? So, and from the graph, if you draw this graph of this absolute value of x, you have this line segment here, right? Between -2 and 1. Then you can easily identify the maximum value, minimum value. In this case, the maximum value is what? 2, right? So the maximum value it means the y value, right? So you can easily see this is 2, and the minimum value is 0, right? But how do we use this closed interval method to solve this problem? And the first thing we want to do is to identify the critical number. Find the critical numbers. Okay, and in this case, if you think about this absolute value of x, you can write this absolute value of x in two parts. When x is a positive, when x is greater or equal than 0, when x is less than 0, that's a negative x. Right? So we discussed this in chapter 2 when we talk about the limits and those kind of things, right? So you can rewrite your function in terms of the piecewise defined function. So when x is a positive, if you take a derivative, it'll give you 1, right? And when x is negative, if you take a derivative, this will give you -1. But the thing is, if you have this x equals 0, you have a sharp turn here, right? So that means that it's not differentiable. It's not differentiable. This implies the derivative of x is equal 1 when x is greater than 0. When x is less than 0, this is a -1, and f prime at 0 doesn't exist. Okay, the function is not differentiable when x equals 0. And this is something we discussed when we introduced the derivative concept. Make sense? So by this observation, we notice that this is 0, x equals 0 is a critical number, right? So x is 0 is a critical number. And this is the only critical number because when x is positive, the derivative is equal to 1, it will never equal 0, right? And similarly, when x is less than 0, the derivative equal -1, it cannot be 0. So there's no other derivative no other point makes the derivative equal 0. The only critical number is x equals 0, and at this point, the derivative doesn't exist. Make sense? Right? And then at this point, then the next step is what you just plug this critical number into the function, so you get an absolute value of 0, which is 0. And then you also need to figure out the critical the function value at the end points. So we have two end points. So f of -2, which is the absolute value of -2, the result is 1, result is 2, sorry. F of 1 is the absolute value of 1, which is 1, right? So, and based on these three values, you can easily see this is the minimum, this is the maximum, right? So this is the minimum, and this is the maximum. Does this make sense? Okay, and this is exactly what we observe from the graph, right? So this is the maximum value, which is 2, and this is the minimum value, which is 0. Okay, so that's this example. The next example is the trigonometric example. So I know many of you may forget about how to solve the trigonometric equations. So I posted some YouTube video on Moodle. Okay, so if you have a difficulty solving the trigonometric equation, make sure you go over those. So in this case, we want to try to we use this closer interval method again, right? So the first step, we try to find the critical numbers. So we do we take a derivative. So this will be what's a derivative? -2 sine of t plus cosine of 2t times 2. Okay. And the second part, you need to use the chain rule. Okay. So we know this is a trigonometric function, which is continuous over the whole domain. Okay, or over the whole real life. That means that this function is continuous on this interval. So the closer interval method applies in this case, right? So and then the first step, we want to find the critical number, meaning you want to find either the derivative doesn't exist or the derivative equals 0. But in this case, because this is a trigonometric function, it's always defined, right? So there's no such point that the derivative doesn't exist. So we can ignore that part. We only need to figure out the derivative equals 0. Okay. Does this make sense? Okay. So, and then how do we solve this equation, right? So the idea is we have this sine t here, and we have cosine 2t. They are different angle, right? So usually it's difficult to solve if you have a different angle. So the first step is we need to convert one of them into you make sure we are dealing with the same angle, right? So the easiest thing is to change this cosine 2t into some function depending only on t, right? And this is what we call the double angle formula. Okay, we use the double angle formula. So the double angle formula have several forms. So in this case, we can write a cosine of 2t is equal, what do we do? 1 minus 2 sine square of t. Okay. So there are several ways to write this cosine 2t. Cosine 2t equals the cosine square of t minus the sine square of t. And you can also write it as 1 minus 2 sine square t, or 2 cosine square minus 1. But the reason I use this as sine t is because the first term is involving this sine function, so I use this guy. So once we have that, we can write this is 2 times the sine of t and plus 2 times 1 minus 2 sine square of t. And the whole thing equals 0. Does this make sense? Okay. So we can divide by 2 on both sides. These 2 get canceled. And so eventually we get, if you multiply -1 as well, so you will get a 2 times the sine square of t plus sine of t, and then -1 equals 0. Right. And then next, in order to, so we need to solve this equation, right? And this equation, if you notice, this is sine t here, if you do a substitution, right? So if you think a sine t is some unknown value u, and this is a 2u squared, it became a quadratic function. Right? So say let u equals sine of t, and then this equation became 2 of u squared plus u minus 1 equals 0. This became a quadratic function. And for this quadratic function, how do we solve it? Well, there are a couple of ways you can solve a quadratic function, quadratic equation, right? So you can use quadratic formula, or you can use factorization. You can factor this. Okay. So in this case, you can write as 2u, I think it's a 2u minus 1, u plus 1. Yeah. Okay. Make sense? So this implies a u equal what? 1/2 and -1. Okay. You get 2 values. U equal 1/2 or u equal -1. You agree? Okay. So, but this is not the event, the point we are looking for. We are looking for the value of t, right? So we know u is equal to sine t, and this implies, so this actually implies sine of t equal 1/2, or sine of t equal -1. Okay. However, if you notice it here, we are looking for the t value in this particular interval. Okay, this interval means the angle is in the first quadrant, and for the first quadrant, the sine of this angle cannot be negative. Sine of this angle is always positive if the angle is in this range, right? Between 0 and +2. So this will not So this won't give you any solution in this particular interval. So you can ignore this one, okay? Ignore this equation because t is in the interval 0 to pi over 2. And in this interval, sine of t cannot be negative number. Does this make sense? So you don't have to solve this one, okay? What about this? For which angle t sine of t equal 1/2? 5/6. 30 degrees, okay? So the first equation implies that t is equal pi/6. Remember, sine this trigonometric function is actually periodic. If we don't have this constraint, then you will get infinity many solutions. Okay, there are many solutions. Like a pi/6 or 5 pi/6 or 2k pi plus pi/6 and so on. So, but we restrict ourselves in this interval. Okay, so this is this is simplified things. So in this case, we get we get only one critical number, t equal pi/6. Okay, so the next step we need to do is to find the function value at the critical number, which is 2 times the cosine of pi/6 plus sine of 2 times pi/6. What do we get? Cosine of pi/6 is what? This is a special value, okay, for trigonometric function. So you should know this. Square root of 3/2. Right, so and times 2, you get a square root of 3, and then the next one is sine of pi/3, which is a square root of 3/2. So this is a 3 times the square root of 3/2. That's a f of pi/6. What is the f of 0? Question? No? So this is a 2 times the cosine 0 plus the sine of 0, which is a 2. Okay, and the f of pi/2, this is given by 2 times the cosine of pi/2 plus the sine of pi/2 times 2, which is pi. So sine of pi is 0, cosine of pi/2 is also 0. Okay. So now which one is the maximum value? Which one is the minimum value? Huh?
Is the maximum?
This is the maximum? 2 is the maximum? Or this one? So that's a trick to compare, okay? So how do we compare these two numbers? We don't have a calculator, right? So like a 3 square root of 3 is the same as the square root of what? If you move this 3 inside, 27, right? And then divide by 2 is the same as divide by what? Divide by 4, right? So this is a square root of like more than 6, right? So it's greater than square root of 6. And what is 2? If you write it in terms of the square root, that's the square root of 4. Now, which one is bigger? Huh? The first one, right? So this is the maximum value, and this is the minimum value. Does this make sense? Okay. Okay, so in summary, okay, I don't want you guys to get lost in the solution process. So you need to understand the procedure, okay, the main procedure. The first step, you find the critical numbers, okay, find the critical numbers. And then after you find the critical number, you plug the critical number into the original equation, find the function value, and also plug the endpoints into the function, you get the function value, and then you compare those values and figure out the maximum and minimum value. So this is what we call the closed interval method, right? Make sense? All right, any question before we move on? We're done for this section, okay? So the next section, we are going to discuss this mean value theorem, right? What does this mean value theorem say? Okay, so the mean value theorem basically tells us that if we have, so the first condition, this function must be continuous on a closed interval, okay, on this closed interval. And then the second condition, this function should be differentiable. Should be, you should be able to find the derivative over the whole interval. So like the previous example, like absolute value in the interval between -2 and 1, it doesn't work in this case, okay? So the mean value, the condition for the mean value theorem is the function is continuous on the interval, if it's differentiable on the interval, then the conclusion is that there must be at least one point between A and B, such that the derivative at this particular point is equal f of B minus f of A divided by B minus A. Okay, so if you just look at this statement, it may be difficult to understand, but if you look at the geometric meaning, and this makes sense, right? So what does this mean? F of B minus f of A divided by B minus A. Slope of what? Slope of the secant line connecting the endpoints. Okay, so if you have A, B here, right? So f of B minus f of A divided by B minus A. That's the slope of the secant line. That's the slope of this line. The left side is the derivative at a certain point. The derivative, remember, the geometric meaning of the derivative is what? The slope of the tangent line, right? So what does this mean value theorem tells us is that if the function is differentiable in this interval, then this function must have a particular point in between such that the slope of the tangent line at this point is the same as the slope of the secant line between the endpoint. Does this make sense? Right? So if the the slope of the tangent line and the slope of the secant line, if they are the same, that means the tangent line equation and this is secant line equation, they should parallel to each other. They should have parallel to each other. That's the geometric meaning of this this mean value theorem. Okay, here is another example. Okay, we have a point, the beginning pointer here. This is the A, and the end point B here. Okay, the secant line connecting these 2 points is this line, right? Okay, and in this case, you can find a line here, which is a parallel to the tangent line, which is a parallel to the secant line. There will be another line over here, which has a slope of the tangent line parallel to this secant line. So this is also stated by the mean value theorem. Okay, so remember the mean value theorem only tells us there's at least one point. It doesn't tell you how many points we have. We may have 2 points, or maybe 3, or maybe more, right? But there will be at least one particular point is suited by this condition. Does this make sense? Okay. So this is the statement of the mean value theorem. A particular a special case of this mean value theorem is this what we call the Rolle's theorem. The Rolle's theorem is a special case. Same condition as the mean value theorem. F of x is continuous on the closed interval, and the function is differentiable on the open interval. But in addition, if we know the function value at those 2 endpoints are the same, so f of a equal f of b, what we conclude is that there's at least one point such that the derivative equals 0. Why? Because if you look at the mean value theorem, if f of a equal f of b, what do we get the slope of the secant line? Should be 0, right? Because if you look at the right hand side of this this equation, right? If f of a equal f of b, this equals 0. Okay, and what does this mean? Is that by Rolle's theorem, if we have a function which is differentiable on the interval, if the end points have the same function value, then there's at least one point in between such that you have a horizontal tangent. Okay, so the difference between the mean value theorem doesn't require these 2 end points to be the same. The Rolle's theorem tells you if you have additional conditions, say this 2-point function value has the same function value here, that means in between there must be a point, at least one point, such that the derivative equals 0. Okay. So, what is the possible application of this mean value theorem? Suppose you're in a moving bus in highway, right? If you take the Salt Lake Express to Salt Lake City, for example, right? At 1 p.m. you pass the mile mark 60. And at 2:30 p.m., you pass the mile mark 140, right? What can you say about the speed of the bus between 1 and 2:30 p.m.? So the speed of the bus may change during this time, right? Make sense? But you can, based on this information, you can certainly say there will be at least one particular moment the speed of the bus should be what? Should be the average, average velocity, right? Average velocity, which is what, 80 divided by 1.3, right? So there would be a particular moment that your bus, the velocity of the bus must be 80 divided by 1.5. Okay? And that's the conclusion you can get, and the idea behind this conclusion is based on the mean value theorem. Okay? So that's all for today. Okay?